just like with the longitudinal modes, it's helpful to have closed form approximations for the lateral modes. And that's really nice when you want to see directly how certain things are related, how certain aerodynamic coefficients or parameters are related to these dynamic modes. So you can figure out what to change on the aircraft if you want to change one of these modes. And so let's look at the roll mode approximation. Here I've got the linearized lateral equations, the lateral eigenproblem. And if we look at, this is an example that I showed earlier where, these are example eigenvalues and eigenvectors. So let's look at this roll mode. And you'll see that if we look at the components of this eigenvector, the roll mode is really dominated by this change in roll. And changes in yawing rate compared to rolling rate are very small. And changes in beta are also very small. So what we're going to do here is we're going to assume that we can neglect beta and r. So what that does is it knocks out our dependency on these two columns here in our eigenproblem. Okay, so we're basically saying those two columns don't really matter. And so what's left, actually, this second row now just simplifies. We've got a CL P bar, an RXX, and a chi of P bar. And so what we can write that as CL comma P bar minus lambda times RXX, and that whole thing multiplied by chi of P bar equals 0. So that's that second equation now. And again, one of the solutions is that chi equals 0, but that's the trivial solution. The non-trivial solution here is the one that we're looking for, and that's where this term here is equal to 0. Okay, so we just set that equal to 0, and what we get here is that lambda is equal to CL P bar divided by RXX. Okay, so that's our dimensionless eigenvalue for roll, and then from that we can get a damping rate, so a dimensional damping rate, which is equal to minus 2 V naught over BW times the real part. This is just a real number. Notice that there's no imaginary component because these two things here are both just real numbers. So we divide those, all we have is a real component, and so it's going to be 2 V naught over BW times CL P bar over RXX. And if you plug in what RXX is, remember RXX is some ratio, and actually it has a wingspan BW in it, and a factor of 8 in it. Anyway, once you cancel all that stuff out, you can simplify this to minus rho times SW BW squared V naught over 4 IXXB times CL P bar. Okay, so this is this is kind of our final expression here. This is the damping rate of the roll mode. And so what we find here, which is not terribly surprising, is that this is basically completely dependent on our roll damping derivative, right? So if we want more damping, then we need to have a larger roll damping derivative there. And then that will be scaled by this stuff out front to give us our actual dimensional damping rate. And of course, from this, then we could compute the time to half amplitude or the 99% damping time. The same types of things we can compute from any of these damping rates. Okay, so that's a closed form approximation for the roll mode.